And so we want to see how is the effect of shorter waves on this dispersion relation, which implies that we need to look at higher order terms in K. So if this is a long wave instability, then let's say after all, this result is an approximation within the context of the Darry-Landau, and we want to include the effect of diffusion, so we have to incorporate the higher terms in K. And I'm going to just summarize the result. So for planar flame, one obtain a dispersion relation which involve, in addition to the Darry-Landau result, which is proportional to K, also a term proportional to K squared. Okay? And this term includes, in fact, three effects that I will describe here. All the coefficients B1, B2, B3 that discuss these effects or that represent these effects are function of thermal expansion, sigma, and depending on the temperature-dependent transport law that you are using. In other words, lambda of T, if you are using a constant conductivity or a function T to some power and so on. So the result is that the first term is the effect of heat conduction. And since, as I noted here, all these coefficients are positive, then being positive with a negative sign in front, it means that that term is a stabilizing term. It reduced the growth rate, so it's stabilizing. So heat conduction have a stabilizing influence on the flame, always. In the same thing about viscous effect. Viscous effect being represented by two different viscosity, a higher one for the hotter burned gas, right? Because of that difference, you obtain a coefficient here, which again, it's always positive, and so viscous effect are always stabilizing. In fact, if one assumed that one ignore the change in conductivity, which is the same thing as ignoring also the fact that the viscosity change across the flame, then you find that this B3 is equal to 0. Okay. So, and the third term, which is in the middle, which is probably the most important one, is due to mass diffusion or species diffusion. And that term is proportional to the difference between the Lewis number and 1. Now remember that that Lewis number is what we call the effective Lewis number, which is the Lewis number of the mixture weighted where the deficient component in the mixture is weighted more heavily. So for a lean mixture, it's going to be the Lewis number of the fuel. For a rich mixture, it's going to be the Lewis number of the oxidizer. And for in between, it's going to be some average value that has different weights depending on the two components. So species diffusion tend to be stabilizing when this coefficient is positive and destabilizing where it is negative. And this is exactly in accordance to the thermodiffusive effect that we have just discussed before. So we see now the combined effect. So in terms of the growth rate as a function of the wave number, this is the picture. This is the Darry-Landau instability, which show that the growth rate increases for all wave numbers, for all wavelengths disturbances. However, when the Lewis number is bigger than some critical value, where diffusive effects are stabilizing, then what we see is that the curve go back and become negative. So the very short waves, the large K, are now stabilized by diffusion, but the long wave remain unstable. Now, if your apparatus or your burner has a certain size which dictate a certain value of K, then if the K fall here, because the K is the reciprocal of the dimension, right? It's the reciprocal of the wavelength, then the flame will always be stable. Otherwise, it will be unstable, and the instability will be primarily due to hydrodynamic effect. On the other hand, if the Lewis number is less than a critical value, remember in the thermodiffusive picture, it was approximately, the little l was like -2, so it's below some value, then then the short wavelengths further destabilize the flame. In other words, you see, in addition to the hydrodynamic instability, also thermodiffusive instability. Okay, so if you like, on this graph that we have seen before, essentially, instead of the red curve, which was obtained for constant density, you are going to obtain now like a blue curve here, where the long waves, namely the k, which are small, are always unstable due to hydrodynamics. Okay? And this is a numerical result of these neutral stability curve, where you see that stability is always above some critical k. But what I really, I will quickly mention here two things. What you can examine is the effect of gravity and effect of strain, like in a counterflow. And in both cases, you see that they may eventually stabilize the flame. So they stabilize those long waves that by hydrodynamic effect are unstable. I don't want to dwell into this too much because I want to move on to the next topic, finish this quickly. This is a similar result, but for spherically expanding flame. You see we introduce a disturbance on the flame surface, and the results are quite similar to what I've described before, the hydrodynamic effect, and then diffusion effect, the stabilizing effect of heat conduction, mass diffusion, depending on the Lewis number, and viscous effect. But now, in a spherically expanding flame, what we see that the growth rate, which is described by 1 over a dA dt, A is here the amplitude of the disturbance, remember, behaves like this. In other words, initially, it decreases and then it starts growing. Because remember that this flame is constantly expanding. And so a small disturbance on the flame, even if it grows, relative to the growing flame is not going to be seen. The flame is growing at a faster rate. And so when a flame is growing at a faster rate, the relative growth of the disturbance first decreases, and then eventually it will increase. So what you expect to see is that small flames, this is a growth rate as a function of the wavelengths of the disturbance, small waves, in this case up to 16, say, millimeter for the condition or for the data that we have ran this result, will be seen as stable, but eventually they will become unstable. So as the flames start growing, it's first stable and then become unstable. This is all under the condition that the Lewis number is above this critical value. Because if it's below, then it's always unstable from the early stages when the flame has the size of the flame thickness. And this is observed, for example, in this picture. You see, this is these both flames were actually done here at Princeton in the lab of Professor Law. They are for lean and rich condition at the same pressure. And so they correspond to Lewis number less than the critical number and Lewis number bigger than a critical number. Even though the flame size is approximately the same, you see that this flame is highly unstable and this flame is quite smooth and still stable. And so the flame corresponds to lean and rich hydrogen-air mixture taken at the same, as I said, the same pressure. The lean one is effectively a Lewis number below the critical value and therefore is diffusively unstable, and the rich one is smooth and stable. Now, the rich one will, if it keep on increasing, it will eventually be unstable at some critical radius, and the instability then will be the hydrodynamic instability. Now we can actually see that we can enhance the hydrodynamic instability if we increase the pressure. The reason is that the term that was multiplied by k squared, which is the stabilizing effect of diffusion, was of the order of the flame thickness. In fact, if you look carefully at the expression, it's multiplied by the flame thickness. At higher pressure, the flame thickness is smaller, so the stabilizing influence are going to be less effective or less affecting the flame behavior. And you see that at high pressure, at 20 atmosphere, the same flame, which is still with the same high Lewis number, it's already unstable. And this instability is hydrodynamic in nature as opposed to this one that was thermodiffusive in nature. This I discussed. I'm going to skip this and go to nonlinear effect. So what is the consequence of the Dario-Landau instability? So the Dario-Landau instability, as we have seen, if we start with a planar flame, we see that the flame become unstable. Yes, under some condition, the short waves are stabilized by diffusion, but the long waves still exist. And so what do they develop to? And so this is what is seen in this diagram, or in this graph. So first of all, the length of the domain here is changing, the length of the integration domain from 1 to 2 to 4. And the critical wavelength for the flame to become unstable is 1.7. So, and remember that this is a mixture which is not which is thermodiffusively stable, right? In other words, the instability is hydrodynamic instability due to the Dario-Landau effect. So if you start with a flame which is slightly perturbed, and all these are different curves that are presented for different time, as you proceed, the flame would evolve as shown, and in fact will flatten out and will propagate at a speed which is computed to be 1 meaning the laminar flame speed that was used for scaling the velocity. So the flame is stable here because the domain length 1 is shorter than the most unstable wavelength, okay? The wavelengths that destabilize. The critical value of the wavelength that the flame is unstable to is 1.7. But if we increase the domain above 1.7, what we see is that the flame eventually develop into this cusp-like behavior and keep on propagating steadily in this fashion. In fact, the solution of this numerical calculation is such that the flame is equal to minus ut plus f of y. F of y, in fact, represent the shape of the corrugated flame, and u is the propagation speed, okay? Such solution were obtained numerically as the long-time behavior of the system. And so we see here that the propagation speed is larger, of course, is 1.08. And if we increase the domain further, the propagation speed is yet larger, and you always develop this one cusp structure. And this is what we refer to as a bifurcation diagram. It's a diagram that tells you what is the propagation speed as a function of some parameter that represent the instability. And the parameter here is effectively, well, it's referred to as gamma, or it's denoted by gamma, but is essentially the length of the domain L, as we have seen in the previous calculation, divided by the Markstein length. The Markstein length, remember, contained the Lewis number effect. Okay. And so what we see is that, let's focus, say, on the red curve. What we see is that until you reach a value, a critical value gamma, which is here approximately 110 or so, 115, the flame is stable and propagate at the laminar flame speed, 1. Once you cross this critical value, for example, by increasing the domain or decreasing the Markstein length, meaning decreasing the Lewis number, then the flame developed this cusp-like behavior that I just have shown you before and propagate at a larger and larger speed than 1. In fact, after a while, it reaches speed, this more or less asymptote here to some value, and you see that the speed can be about 20 to 25% larger than the laminar flame speed. Of course, this large propagation speed is due to the larger surface area of the flame, and that is essentially the consequence of the Dario-Landau instability. This is just a detailed picture of two such flames that I shown you before. this one propagating at a larger speed than this, and it's also more pointy towards the burned gas than this one, where here the curvature is somewhat smoother. Of course, it's much more significant than what you see here, the difference between the two, because this has been scaled on the same length L, whereas it's supposed to be corresponding to a wider flame, and so in principle it will be more cusp. The cusp will be more sharper. This is a direct numerical simulation of a flame that is also hydrodynamically unstable. This is done for hydrogen air, using a one-step chemistry, and you see that after some time the flame developed into a one cusp-like behavior and continue to propagate to the right, and that structure does not change. Okay. This thermodiffusively unstable flame, let me see if I can get the movie. I have to move out from where I am. Okay, just a second. Okay, so now we are looking at the, again, hydrogen air flame with, in fact, detailed chemistry, but a flame which is, the Lewis number is, oh, you've seen it already. I wanted to describe it first. So this is a flame, I'll run it again. So this is a flame which is thermodiffusively unstable because the Lewis number is significantly, it's actually lean hydrogen air, and so the Lewis number is sufficiently small. So it's really in the regime where it's thermodiffusively unstable. And what you really see is that initially, what you see initially is the small scale, like what you see now, the small scale disturbances developing, which is the thermodiffusive instability. Eventually, this one large cusp-like structure develop, but you always have those small scale that are developing on the flame front due to thermodiffusive effect. The thermodiffusive effect are usually small scale disturbances compared to the more larger scale, which is the hydrodynamic effect. Okay, the next discussion is on diffusion flames, and there is a whole history of, so far we have talked about instability in premixed flame. Diffusion flame have a different character because unlike premixed flames that have a characteristic velocity, and as a result we have seen that because of the propagation the gas expand, and this induced velocity create this hydrodynamic instability. That Darry-Landau instability is not actually present in any significant way in diffusion flame. But thermodiffusive instability have been observed in diffusion flame as well. In fact, I will talk about density effect after first describing what happened here. After first describing the Any reason why I lost the connection to? Oh, you got it? Okay, good. So first I want to describe the thermodiffusive effect in diffusion flame. They have been observed in various situations. For example, this is a diffusion polyhedral flame, as this is a premixed polyhedral flame, but I don't want to discuss those. Let me go through this one, which is simpler. That's the base of a diffusion flame, that was observed when a diffusion flame was created by a splitter plate burner. So you have a splitter plate, fuel coming from one side, oxidizer from the other, and the base usually will be simply smooth and flat, and the flame will develop further downstream. But what was observed is that at high flow velocity, when this was a hydrogen-oxygen flame, and when the hydrogen concentration was substantially reduced, the base becomes cellular, and this is the cellular behavior that you see. Note that the cells are of the size of 1 centimeter, which are significantly larger than, let's say, the reaction zone thickness. Now, this was observed when also the nitrogen in this mixture, which was the diluent, was replaced by argon. But when it was replaced by helium, the flame remained smooth and not cellular. So one of the things that we would like to understand is this behavior. Now, the stability question in diffusion flame, again, will lead mathematically to a dispersion relation that describes the growth rate and the dependence on the growth rate on the wave number. But the parameters that, that are involved in such problem include, first of all, 2 Lewis numbers. And instead of a flame speed, because a diffusion flame does not have a characteristic speed, it's really the Dam-Kohler number that represent the different response or the different flame behavior, right? For example, large Dam-Kohler number would represent a Burke-Schumann flame sheet with complete combustion, complete reactant consumption, whereas a lower Dam-Kohler number will correspond to a flame that have some fuel and or oxygen leakage with a lower flame temperature. And then also it will depend on phi, which is essentially a measure of the mixture strength. We discussed that yesterday. And of course, also the density ratio between the cold reactants, rho u, and the density of the flame, rho f. And so, so the result would involve really many more parameters to examine. So the first thing to see is that the Burke-Schumann that one obtained from such an analysis is that the Burke-Schumann solution of complete combustion, which corresponds to d going to infinity, is always stable. That's not very surprising because you see what you are doing is you are forcing by assuming a Burke-Schumann solution, you are forcing that the fuel and oxidizer have to be completely consumed at a reaction sheet, which is located usually at the stoichiometric surface. Now, suppose that the flame sheet is slightly disturbed. Well, the only location where fuel and oxidizer can be completely consumed is at the stoichiometric surface. The sheet, therefore, as it's perturbed, must eventually go back to that surface because that's the only location where both reactants are completely consumed. So as long as you are forcing the solution, in other words, as long as you are insisting that the Burke-Schumann solution exists, the flame will be stable. And that's what the results show. So that's not surprising. However, when instability develop, they usually develop near the extinction point, which would correspond to high flow rate, because D is, as we spoke yesterday, is inversely proportional to the flow velocity. You increase the velocity, you decrease D. Okay, so instability develop only in this region, and essentially they can be controlled by, they are essentially predominantly thermodiffusive in nature, and they are controlled by the 2 Lewis numbers. So this does not mean that always that segment of the S curve is unstable. All I'm saying here is that if instabilities occur due to variation in Lewis number or mixture strength, then they will develop in this region. Okay, and so this is a graph that shows where you would expect to observe stationary cells, and they will be observed usually in a region where the Lewis number of the fuel and oxidizer are typically less than 1, and in a region like this you will expect pulsations. I want to move faster because I am a little bit behind. So here is the picture or the figure that I showed you before from Dungworth and Melvin from '76 of the hydrogen-oxygen diffusion flame diluted with nitrogen. Now remember the result that I mentioned, which are written here again. and the condition when they observe this cellular base. First of all, they observe it only at high flow rate. High flow rate corresponds to D below some critical value, as we just talked a minute ago. Second thing, they observed it when the diluent was nitrogen and argon. Now remember that the diluent can affect two things. It can affect the thermal diffusivity of the mixture, because essentially the mixture thermal diffusivity is determined by the abundant species, which is the diluent. And the second thing, it would affect the molecular diffusivity, which is in the denominator of the Lewis number, because the relevant diffusivity is the reactant, the binary diffusivity between the reactant and the diluent. So changing the diluent will change that as well. And so if you choose nitrogen and argon, you find out that the Lewis number of the fuel is low enough, and it's in the range where instability are observed. However, in helium, the Lewis number of the fuel is quite large. It's close to 1, and so it's no longer accessible to the instability. And so that's totally consistent with the experimental observation. In other words, this theoretical results are consistent with the observation. Another thing to note is that the theory showed that the cell size are typically 1/2 to 2 centimeter, and we have seen, at least in this figure, that it's indeed within this range. This is another form of instability, which, let's see, this, no. If I believe that that's a movie, let's see if that works. Yeah. And this is a pulsating instability. You see, the only change that was done in this jet flame from a condition where it was stable and stationary, it was just changing the concentration of the fuel, changing or adding, diluting the mixture further. And by changing that, it was changed to a range where the Lewis number was sufficiently large and oscillation were developed. The flow remained just time independent. It's simple flow. It's just that the flame is oscillating back and forth. And the Lewis number for, well, it's not written here, but I think it's in the next slide. Yeah. So here are the range of the Lewis number where these oscillations were observed. This is, by the way, the jet flame which was not oscillating, okay, was steady and stationary. And when oscillation were developed, it was always under condition when the Lewis number was, one of the two Lewis number was sufficiently large, but the mixture strength was significantly high. And so that's another effect that was mentioned here that I did not discuss as I was moving these transparencies. Instability are predominantly thermodiffusive. Oh, it's not here. Well, anyway, what I wanted to say is that the parameter phi, which is the mixture strength, pulsations are usually observed when the mixture strength is large, which means that the system is more rich. And when I say more rich, because this is a diffusion flame, it's rich or lean is based just on the boundary condition, on the condition at the supply end. And cellular instability is usually observed when the system is relatively lean, which means phi less than 1. Okay. This is a cellular diffusion flame on top of this unstrained planar diffusion flame that we also discussed yesterday. And the condition here, again, agree with the result from the theory. Note that, again, the size is approximately 1 centimeter, which is within the range of what we have predicted. And this is essentially a pulsating flame, which you can see here. It's a planar pulsating flame. Oh, it didn't run, so try it again. well, anyway, it's what you would have seen in the movie, that it starts oscillating up and down. And in fact, this is more convincing really than in the movie, because in the movie you see some side effects that are not very clear. But what you see here is that the flame position that going through a limit cycle. And so many of the instability that we spoke in the previous hour for premix flame are also observed in diffusion flame, but under slightly different condition. Now this is again a diffusion flame, but in a tubular reactor. You see the flame is in principle a cylinder that it's elongated, and it's stretched in the axial direction. You see the flow field is shown here. And so in general, the flame, in principle, the flame should be smooth and just you should see a circle. In fact, this flame is a full circle. The only reason for this area here, it's some instrument or something about the photograph was just setting on that in this area, and so it blocked the view. So this was a smooth flame that eventually became cellular, as you see here, and the number of cells and so on depend on the strain rate and so on. So just to see another form of this instability. Finally, the effect of density variation. As you recall from the last lecture, density variation, which is the source of the hydrodynamic instability for premix flame, is very significant. As a result of the change in density, the flames are highly unstable hydrodynamically. Now, the question is what happened for diffusion flame. So I'm going to show you two results, one for cellular flames and one for pulsating flames. So this is the growth rate as a function of wave number for cellular flames. And what you see then is that, say, the green curve is a stable flame because the growth rate is always negative. And then, you know, when it goes above the axis, then there is a range of wavelengths where the flame is unstable. And the difference between these curves is just changing sigma, which is the density ratio. So as you increase the density ratio, you know, the thermal expansion cause a flame which is essentially stable to become unstable. So on cellular flame, the effect of density changes is to further destabilize the flame. I maintain that the origin of the instability is diffusive thermal in nature, but the effect of density allow the flame to be sustained or destabilize the flame further. Well, this is a graph that showed the vorticity field on a cellular flame, but I'm going to skip that. This is the next one, which is the effect of density variation on a pulsating flame, diffusion flame, okay? And what you see here, it's very interesting that, in fact, as you increase sigma, the growth rate or the flame becomes stable. So the effect of density variation on a pulsating diffusion flame is to stabilize the flame. Okay. Now, I don't know if I have that figure. No, I don't have that figure. You see, there is a difference between premix and diffusion flame. In a diffusion flame, the temperature peaks at the reaction sheet, right? And so the density decreases near the reaction sheet, but then it increases to the two other sides. So what happened is a pulsating flame start oscillating, but on either side that it go, it has an increase in density which causes a damping on the flame rather than enhancing the instability, it slows it down, okay? And that effect is not, of course, present in a premix flame, because in a premix flame, the density just vary, in other words, the gas expand, the density decrease in the burn gas, keep on decreasing further and further. So with this, I really finished the discussion on stability, and what I want to move on is We have about half an hour. But so I want to move on to turbulent flames, and I am going to be picking and choosing a few of the slides only because I want to discuss more the turbulent flame speed, which is in the next lecture. And so, let me... Okay, so the few things I want to emphasize is, first of all, something about turbulent scales. And then the only other thing I will discuss from this lecture is the diagram of different turbulent flames or regime of premixed turbulent or turbulent combustion of premixed gases. So one thing in turbulence is that we often said that the turbulent flow is made of eddies. And there is no precise definition of what an eddy is, but roughly speaking, an eddy is a macroscopic fluid element which behave as a unit, okay? And it must be behaving as a unit, therefore it must be identified by some scale and by some velocity. And so it has a characteristic size and a characteristic velocity. Now, a number of small eddies are usually embedded in a large eddy, and that's the nature of turbulent. Now, there are different scales that you can observe in a turbulent flow. The larger scale will be the scale of your combustor. So let's say the size is capital L. And then the velocity that is representing the overall motion, say the mean velocity in your combustor, is going to be capital U. That immediately gives you a Reynolds number that you define as UL divided by nu. Nu is a kinematic viscosity. But this is not what we call the turbulent Reynolds number. The turbulent Reynolds number will be defined soon. Before we define this, let's talk about this correlation function. So R is a correlation function. In other words, if you, it is defined as such. If you take a point x and another point which is distance r from x, right? So you have 2 points, x and x plus r, and the prime is the fluctuation from the mean. So when you have a turbulent flow, you can describe the mean flow plus a fluctuation. And so U prime is the fluctuation at point x, and U prime at x plus r is the fluctuation at the other point. And now the question is, are these 2 points correlated? In other words, is there any correlation between the two velocities at these 2 points? So the correlation function is determined as the product of this, the mean of the product. And if you want to normalize it, then you divide by the mean square. So this is the F, which is the normalized correlation, okay? Now, if the points are at the same point, they are fully correlated, clearly. So F should be exactly 1, because it's normalized. If they are very, very far apart, F would go to 0, because they are totally uncorrelated. So the function F is a function that starts at 1 and decreases to 0. Out of this function, we can define a length. The length is going to be the integral of this correlation function F integrated from 0 to infinity. In other words, the area under this curve will be equal to the area of this shaded area of length L. And so L is essentially what we refer to as the integral scale, okay? And it's a representation of certain eddies in turbulent. Okay, this is just to say that the fluctuation V is related to the kinetic energy, and that's the relation. Now, if you have an integral scale L, and you divide it by the, and you divide L by the intensity, the turbulent intensity V prime, that gives you a time scale, and this is the time scale, the turnover time of these eddies, of the eddies of size L. Okay, now let's see. Okay, now before we define, so So in a turbulent flow, you have eddies of different sizes. And the idea which was set by Kolmogorov is that you have the large eddy that essentially carry the energy, and they transmit it to smaller eddies which still carry energy until the smallest eddies where the energy is dissipated by viscous effect. And the smallest eddy are referred to as the Kolmogorov, or they are of the size of the Kolmogorov length scale, which is denoted here by eta. So we start with the motion of, so the very small eddies will be much smaller than L, and so they will be represented by this scale eta, which is the Kolmogorov scale. And this is the range, essentially the inertial range, the range of length scale of interest between Kolmogorov and the inertial range L. Now, what I have shown here is essentially the Kolmogorov scale, the corresponding Kolmogorov time, or the time scale corresponding to this Kolmogorov eddies, eta, and the velocity scale, or the Kolmogorov velocity. And they are all related to the energy dissipation epsilon, which if epsilon is the energy dissipation, it will have units of meter squared per second cube because of essentially its energy, which is velocity squared divided by second, right? It's a rate. If you divide, and so if you use the kinematic viscosity, which has units of meter squared per second, you can create a length which will be the Kolmogorov scale, because it's essentially those scales that the energy is dissipated at. This was just the definition of those scales. And all I wanted to show here, you can read the detail further, is that you can relate those scales to essentially the turbulent Reynolds number. For some reason, I thought I had defined the turbulent scale somewhere, and I don't see it. But essentially, is defined, where is it? Ah, maybe it's before. No. No. It's here? Where? Oh, here. Sorry. So the turbulent Reynolds number is defined with the integral scale L, the fluctuation velocity divided by nu, the kinematic viscosity. And then you can define the ratio of the two scales, the Kolmogorov scale to the integral scale, the Kolmogorov time to the integral, to the time, the turnover time for the corresponding to L, and similarly the velocities. And they are related to different powers of the turbulent Reynolds number. Okay, I was going to skip those, but come back to this diagram. The diagram is start from this discussion here. So there are different regime of premix turbulent combustion, and the first that have discussed this was Damkohler, and Damkohler identified two limiting regime: small-scale turbulence and large-scale turbulence. In large-scale turbulence, essentially the flame is very thin compared to the smallest turbulence scale, namely the Kolmogorov scale, and therefore it's unaffected by it, okay? And so the turbulence-flame interaction is purely a kinematic one. On the other hand, in the small-scale turbulence, the eddies can affect the internal structure of the flame, and so affect the flame as well. So those are the two range that Damkohler discussed. Now, they will correspond to different regime that we refer to today, and that the diagram of which I will discuss in a minute. So in order to discuss this different regime, we want to relate essentially, we want to present it in a diagram that represent intensity of turbulence as a function of turbulent scale or integral scale. That's the diagram that we want to present. So let's first build up some of these expression before we go to the diagram. So the first thing is that all diffusivities do not vary by much and can be treated, at least for this phenomenological discussion, as constant. So thermal diffusivity and the mass diffusivity or binary diffusivity of the fuel in oxidizer, they are all can be denoted by D. As well as nu, which is the kinematic viscosity or diffusivity of viscous effect, also can be treated as equal to D. So nu is D, and so all these are of the same order, and we are going to call them D. Now, the flame thickness is, we have defined it to be the thermal diffusivity divided by the laminar flame speed, and so it's essentially D divided by SL. That's the length of that's the thickness of the flame. The time scale or the residence time scale in the flame is going to be defined as the time scale which is correspond to this length divided by SL, so it's going to be D divided by SL squared. And now remember that we have defined the turbulent Reynolds number as LV prime over nu. That implies that the turbulent Reynolds number can be written as the product of V prime over SL times L over the flame thickness, okay? And those are the two factors that we want to represent in our diagram. So in particular, the Dam-Kohler number, which is the flow time divided by the reaction time, it's going to be equal to the product of L divided by LF multiplied by SL divided by V prime. So in a diagram which is intensity in this scale and the length scale here, right? Integral length scale represented in terms of the flame thickness, and this is represented relative to the laminar flame speed. The two relations that I just derived here, the Reynolds number and the Dam-Kohler number, they are written here again. They will represent two regions. One region where it is turbulent flow as opposed to laminar flow. Turbulent flow is when the Reynolds number is sufficiently large, let's say larger than 1. And larger than 1 means that V prime over SL as plotted against L over LF, it will have it's going to be the inverse, 1 over the other, right? Multiplied by this, but this is 1, so it's 1. Now, this is a log-log plot, so being proportional to each other, being in the power -1, it's essentially a straight line with a negative slope, right? So this in the log, right, in a log-log plot, it's going to be this line. That's the Reynolds number 1. 1 equal to this will be represented by this line. So when it's below 1, you expect laminar flames here, and turbulent flames will be everything above. Now, the Dam-Kohler number distinguish between small scale and large scale, as Dam-Kohler represented, right? And so the Dam-Kohler number, it's essentially, you see, it's going to be a line with, no, I'm sorry. So the Dam-Kohler number will be essentially when V prime over SL is small, D is small. D small is like a region of well-stirred reactor, right? Flames are usually high Dam-Kohler number, right? Because high Dam-Kohler number means a very quick or very fast reaction time. And so flames will be usually in this region, as opposed to a region here where the turbulence will intrude inside the flame, and really there is no a flame. There is a region where combustion occurs throughout. Okay, so this is one of the distinction. And then the next few distinction, and I want probably to skip some of these details, is represented by a Karlovitz number, which is represented here. And actually, there can be two Karlovitz number. Now, the Karlovitz number was defined here, which is essentially the the resident time inside the flame, TF, divide by the Kolmogorov time, or the residence time inside the flame, where is that? Yeah, no, I mean, this is the Karlovitz time. In other words, it's going to be a measure of if eddies do penetrate the flame structure, not the reaction zone, but the flame structure, and affect it, or do not. But then you can also define a Karlovitz number on whether the eddies penetrate inside the reaction zone. So this is really the difference between these two curves. So what you have, if I summarize this, in this turbulent flame regime, you have first a region that the flames are simply wrinkled. Then you have a region where they are highly corrugated, they can fold, right? The flame surface can fold, create pockets of unburned gas that will detach from the main flame surface, burn by themselves, and so on. This is the corrugated flame regime. And then there is a thin reaction zone regime where the flame is, the preheat zone of the flame is affected by turbulence, but the reaction zone is not. And then there is a region where even the reaction zone are affected by the flame. And just to make a better understanding of this, I will show you some simulations that correspond to points A, B, C. Note that at the moment we are in the wrinkled and corrugated flame. And then we are going to see points which are above that. And the simulation were for integral scale of that range, approximately. Okay, so here are the three values of the Karlovitz number as we go, A, B, C. The first one, the flame is slightly wrinkled, but no more. On the left, by the way, what you see is reaction rate contour or fuel consumption rate, and on the right is temperature. So that's what the distinction between the two panels. Now, B is a case where the flame is corrugated now, and C was, if you remember, C was, well, oh, B was still wrinkled, but, you know, the wrinkle was more affected, in other words, larger wrinkles. And C was in the corrugated flame regime. So you could see a difference between this. This is very weakly corrugated, highly corrugated, and then this is in the I'm sorry, I say corrugated, I meant wrinkled, and this is more corrugated. Really, the difference is just that as you come here, you see how the flame folds, and whereas here is just a weak wrinkling of the surface. Okay, the next one, as I said, are going to be at this point C and D, which are now in the corrugated regime, and no, we did CC. So the next one is in the thin reaction zone regime, where now the eddies penetrate the flame surface, and you see that they affect quite a bit of the flame surface. The flame is no longer like an interface as it was before. All these calculations were with full chemistry and full simulation. So there is no assumption here of thin flames and so on. So what you saw before, the flame being thin, is just a consequence of it is just burned almost at an interface. Okay, so, and then the last one is the point E, where you are in the distributed reaction zone regime and everything is affected by the turbulence. You don't even, it's hard to even identify a flame surface at all. Okay, so this is the diagram, and I will stop now. Please be on time because I want to try to finish the last lecture. The last lecture will be on turbulent, the turbulent flame speed, so we will move to it as soon as we come back.